Hi everyone, my name is Lydia and this is what I wish they had taught me about econometrics and introduction. We've talked a lot about the OLS and its mechanical properties, and we're about to move into the statistical properties of OLS. But before we can do that, and before we can continue to argue why we like OLS and why it is what we will later on call the blue estimator, meaning the best linear unbiased estimator with the lowest variance, we need to talk about two things, meaning the expectation and the variance. For this, in this first video, we're going to talk about the expectation operator and the properties of it. The expectation operator we've seen in almost all of the mechanical properties and also in some of the works we've done with the OLS. Now, it's going to tell us what happens on average over repeated samples of the world. For some of you, this might be a little bit like, well, I've already seen this. I kind of already know that this expectation operator is giving me the same things as an average. But let me give you a little bit more of an intuition of why do we think of the expectation of a random variable as the long run average value. Okay, so if you had this like repeated data generating process infinitely many times, the expectation operator, it's going to give you that long run average value. So for instance, imagine we have a variable x that takes two values, and it takes the value 2 with a probability of 1/2 and value 8 with a probability also of 1/2. Now, since I am including here probability, it means like I can think of this as in a bigger scale version. Imagine that I have a coin. On one side of the coin, I have number 2, and the other side of the coin, I have 8. It's a fair coin, so probability 1/2 and 1/2. If I flip the coin 100 times, sometimes I will see a 2, sometimes I will see an 8. The probability of me getting a 2 or an 8, it's exactly the same, 1/2. But if I keep doing this 100 times, that what I am seeing is that on average, I'm going to see with a probability of 1/2 a value of 2 and a probability of 1/2 a value of 8, which means on average I will be seeing a 5. Okay, so keep in mind this 5 is not the value you observe today. This is the value you'd see on average across many worlds. Now that I've given you a little bit of an intuition of what the expectation of a variable really means, let's see the properties of the expectation operator. The first property that we're going to see is that the expectation of a constant is always to be the constant. If you think about it based on the intuition that I just gave you now, even if the value that you receive today is a constant, let's say 5, you will all the time see that constant 5, so also on average, you will be seeing that 5, okay? The other rule that we're going to look into is that for any constants, A or B, the expectation of AX plus B is A, the expectation of X plus B. So the part for the B, we've already sort of introduced with the first property that the expectation of a constant is equal to C. However, what's happened in the second property is that we're applying the fact that the expectation operator is linear, which means that we can literally split this bracket into separate elements and have these written as the expectation of x times a plus b. Okay. Now, this is a very, very powerful rule because it means that if you have an expression that instead looks like ax plus by, where y is another variable, then this can be written simply as a, the expectation of x, plus b, the expectation of y. That also means that if instead I had a minus ax minus by, then the minus will be translated also between the items after we take them out of the bracket. Okay? The next and the last property, which is very powerful as well, is that for any constants, let's say we have them running from a1 to a2 and so on until a last one, an. And then we have random variables, x1, x2, and so on until xn. Then we can write the following. The expectation of a1 x1 plus the a2 x2 plus until the very last one. This is going to be exactly a1 expectation of x1 and so on. So this, we're still applying the second property in a sense that we learned. However, I will rewrite it to you in a different way that will be more recognizable to you, especially if you've done econometrics before and you've used that to do different proofs. That means that the expectation of the sum for I going from 1 to n of ai xi is equal to the sum of ai for I going from 1 to n of the expectation of xi. Okay, so the expectation of the sum is the sum of the expectation. Again, very powerful property, and you very likely will see it applied in most of the proofs. Keep in mind, for all of the properties that I have mentioned so far, so we've pulled out the constants out of the expectation operator, we can split the sum, we can split the difference. What doesn't change is that we don't need to make any assumptions on independence. So no independence needed. The reason why I am writing this is because there is another rule that I'm going to add now, but the assumption in here is that x and y are independent from each other. This is not per se a rule of the expectation operator, but just keep that in mind that you might see it and it comes because of the assumption that the x and y are independent. And that is that the expectation of x times y is actually the product of the expectation of x and expectation of y. Okay, so normally the expectation of the product will only be equal to the product of the expectations if x and y are independent from one another. Let's very quickly go through these properties once again before we conclude this video and give you a little bit more of an insight of where you could be seeing it when you use the OLS. So we learned that the expectation of a constant is equal to the constant itself, meaning that if you had the expectation of 7, that is simply 7. For any constants a or b, you're going to have that the expectation of ax plus b is just a expectation of x plus b, meaning that if at some point you had an expression that read the expectation of 3x plus 10, that would literally be 3 times the expectation of x plus 10. And ultimately, the sum, the expectation of the sum being equal to the sum of the expectations, this is a property that you will see in OLF's proofs, mostly when you deal with the error term. So if you ever see the expectation of the sum of the error terms, this is going to be the sum of the expectation of the error term. Why this is important? Because when we move into the statistical properties, we will only be using the error term, not the residuals, and we will have assumptions on the error term, and we will have to use that for different proofs. So expectation is the foundation of all the statistical guarantees in OLS that you will be seeing. Hopefully, we have now built some of those building blocks for you to be able to follow with the statistical properties better. In the next video, we'll build on the second ingredient, the variance operator, which will tell us the spread of an estimator across the repeated samples. I hope this video was helpful, and I'll see you in the next one.